network defense personnel are not quite like the IT specialist that you'll go to if your computer's not connecting to the internet. They're actually involved in the defense of massive cyber infrastructures. These are your power grids, nuclear storage facilities, things of that nature. So, in studying cybersecurity, there are really three components to it. There's hardware, there's software, there's also the mind of the human operator that has to actually run those systems in order to defend a network. Hardware and software development is quite easy and quite quick in comparison to the process of biological evolution that requires around about 900 million years to naturally select for an upgrade for the brain. That's gone a bit fast. So in my project, I've investigated the influence of software design on users' capacity to sustain attention for prolonged periods of time to these defensive systems. So these defense systems, they're known as intrusion detection systems, but a key bottleneck to them is the analyst's capacity to actually sustain attention to the systems that they're monitoring. As a result, what ends up happening is that their attention system is destabilized, and that looks like a compounding in the rate of errors and mistakes that they make over time. It's known as vigilance decrement. You'll also see that in things like truck driving, for example. The longer that you're driving, the more errors that you might make over time, just the brain is tired. So vigilance decrement is seen in cognitively demanding tasks that require repetitive and monotonous processing of large volumes of information. The effect is caused by cognitive elements of a task that effectively dysregulate the regulation of nutrients within the human attention system. It's actually this area right here. It's your anterior frontal lobes. So the purpose of my PhD was to investigate cognitive elements of design in intrusion detection systems, those defensive softwares, that cause that destabilization of the attention system. So your brain has two sources of fuel, effectively. The first is glucose. That is what is primarily delivered through blood, and it's its main go-to nutrient. But it's also got glycogen, reserved in small cells called astrocytes. They hold onto it very much like a spare fuel tank. So I'll show you how those things work. So on the graph on the left, we have what your brain will achieve. Oh, that's not working. So this is what your brain does at lower levels of performance. When it's not, when the level of cognitive demand is not particularly high, you'll see some level of fluctuation in your attention capacity, but it largely stays around a certain level. It's only going to end up using this glucose, that thing that comes from blood. There we go, it works the second time around. And again, it will hover around about a certain level. But as is the case in network defense, when they're using that defensive software, this is what happens. It necessitates a much higher degree of brain activity, but it's also prolonged. So the brain can reach that higher level as opposed to over here. But in doing so, it draws on that spare fuel tank, that glycogen from those astrocyte cells. But the thing is, once you've depleted that spare fuel tank, well, your capacity is going to drop back down to a level that approximates what it can achieve just with blood-based resources alone. And the problem is, this destabilization can happen in as little as 5 to 15 minutes. It's not very good when you've got an 8-hour-long shift, let alone when you start to consider the fact that these are shift workers who also have to disrupt their circadian rhythms in order to work, say, between 12 o'clock at night and 4 o'clock in the morning. So my idea was effectively to physiologically monitor their capacity for attention. That's me. That's my brain scanner, and that's the system that I developed to simulate what this software does. This brain scanner is called a functional near-infrared spectroscope. It just uses a light to look into the neocortex and specifically the cerebral vasculature. It's looking at how much blood and how much of those resources you're actually using at any given moment in time. It's also known as a poor man's fMRI. But I'll talk a little bit more about that software. So this software I've called the Western Australian Cyber Defence Task. There's really not much work in the literature that's been done towards this sort of task in the past. The United States Air Force has something approximating this, but it's quite antiquated by today's standards. In effect, the task comprises three concurrent components that stress three different parts of your attention system. Your capacity to notice signals, a high amount of workload volume, but this part I'm most proud of is this is something called a metadata threat analysis. So the user will process information over here, information related to what they've just processed, and this parallels what an operational intrusion detection system will do, is then presented over here. The analyst then has to look at that graph and tune cyber threat. So for example, that's a level 1 threat, top priority. These are level 5 threats, effectively noise. But in this example here, I've got two sources operating at the same level of high priority threat. But each of these columns lines up. So that source, that source, that source, that source, they're all aligned. So out of those two top priority alerts, which one should the analyst make note of first? Well, perhaps it's going to be the one that's also paralleled with a lot of low-level alerts. This is something known as a prevalence denial attack, where a malicious actor will attempt to obscure the higher level threat with a lot of noise at a lower level. These are things which can effectively just increase the amount of cognitive load that an operator is on. So they're not essentially hacking the system, although they are. They're also trying to hack, in effect, the defender's attention system as well. If they can destabilize how much attention an operator is using to defend a system, then the system as a whole decreases in its efficacy. So I looked at two different compositions of this task, a static and a dynamic state. So this in effect asks the question, when is an operator more likely to lose focus due to this due to vigilant state? Is it going to be in times of consistency, or rather static, there's not a lot of things changing? Or is it going to be the case that when things go from, say, quiet to very harried, or harried to very quiet, transitional states, are those more likely to cause destabilization of their attention system? So, in effect, both are bad. But, okay, so 2 plots. I'm going to explain this one here first off. So the red is behavioural data that the WACDT tracks, performance metrics. So the red refers to the static task, where things remain the same, and the blue refers to dynamic tasks, where things are changing up and down. And you see very different patterns of results. When things stay the same, people get better. That makes sense, though, because the task isn't changing, they're effectively learning and getting better at it. But when things it's during these transitory types of tasks where people's performance dramatically declines. Now, I can then look over this plot here. This is a plot of the brain scan data for one of them, from one of the participants that we drew. The results have actually been fairly consistent in what I'm about to walk you through. So we've sampled around about 20. We've got 5 people left to go, but it's effectively been the same result every time. So the blue here refers to brain scan data that was recorded during this person's dynamic task, and the red corresponds to their static task, and very marked differences. So during the static task, when they're improving, you just see this downward sort of trend in their brain scan data. Whereas there are some other features that we can point out when they're getting worse. So when they're getting worse, you can notice first there's an initial local maximum, peaks, then it drops back down to a local minimum, and then it overcompensates. It ends up at a point that's higher than here. Whereas their brain scan data, when they're getting better at things, it's almost like their brain is sort of settling into an optimal level, or a more efficient state. Whereas when things are changing, the cognitive resources have to shift quite a bit more around to accommodate the changing task demands. What does this effectively do? What it tells you is that this is now a key psychological indicator for network defense performance. This draws a direct link between psychophysiology and cybersecurity. So what are its applications? Well, the WACDT, first off, produces an anonymized, team-based summary of the behavioural and psychophysiological capacity of a user to actually use an intrusion detection system. So if you're a cybersecurity company and you have one of these very expensive pieces of cybersecurity software, you can calibrate the WACDT. So it's as hard to use as the simulation I've developed. You then run the person through, well, for example, you can run a pool of candidates through the system, and it will tell you, out of that pool of candidates, who has the greatest capacity to actually use the software that you're going to run them on. The benefit to that is you then don't have to show your pool of candidates your actual internal back-of-house software. So in effect, that allows the identification of analysts to perform best under different cognitive loads. Because you can also ask, well, who is it best to have on when things are quiet? Who is it best to have on when things are harried and changing? It could, but more important than staff selection, it could actually inform cognitive elements of the way that these systems are designed in order to optimize compatibility with the actual individual user. So if I go back, this particular participant here had a specific range where, this composition of the WACDT produced improvement, whereas this one produced a degradation in their performance. Well, what that means is that I can then shift some of the cognitive elements of the way that that program is composed. Not what it's showing you, but how it's showing you what it's showing you. So that effectively you get a performing type of brain activity in times when usually you would see their performance suffer. In effect, it's like a tailored suit. The WACDT is the tailor's measuring tape. In addition to that, it also lets you test out different, I call them battle scenarios. So another aspect of cybersecurity that's a concern is it's not done by any stretch of the imagination developing. A new threat can come out every day, every week, every month, every year. It's an environment that's effectively self-selecting for malicious capability as well as benevolent capability. We have good actors in the research space that are trying to work out how to better defend against people on the outside who are being naturally selected for their capacity for cybercrime. But in effect, it takes out the guesswork. How is my team of network defense analysts going to respond to a new and a novel threat that they haven't seen before? Show it into the WACDT, and you can test how they will actually perform under those new and novel, or rather, new and dynamically changing situations. And more than that as well is it allows you to benchmark cognitive compatibility of network defense software. You can ask questions, well, how compatible is this software with my team of network defense analysts? Is it compatible enough? Is there a certain range of it? So the amount of fruit on the tree that this type of software can offer to the cybersecurity research base is quite broad. So the current state of the project, at the moment we're still in testing. We've done 20 out, as I mentioned earlier, 20 out of 25 people have been sampled. The data is anonymized. At the end of each session, they get that anonymized team-based performance metric. But more than this, this current state of the project, it's the state of the science. Cybersecurity is fundamentally a psychological field. You have human engineers designing human spaces for defense against human-based threats. Certainly the tools that they're using are software and hardware-based. But it's also a case that psychology and cybersecurity really should be drawn together. And this project demonstrates that there are key vital signs of a network defense analyst's biology that will inform you about their capacity for work. So that is in effect my project. If you have any questions, I would very much like to invite them now. But thank you very much for listening to my talk.